But
Moving on.
Okay, so...
Ooh, goody.
Yeah, now
Now we're going to discuss the invention of gravity.
Yes, the invention of gravity.
Oh, yeah. Because before this, well, before a certain point, gravity didn't exist.
That's true.
So, now this is going to be a fairly brief history of gravity. Now, I've got to go back to the beginning because the concept has had some evolution over time.
Wait, evolution? You mean like
No, I mean microevolution, not macroevolution.
Okay, all right,
that's totally different thing. That's, my goodness gracious. I'm not one of them heathen types. Okay, first thing you have to think about when you're thinking about gravity, well, there are basically two paths of inquiry that kind of meet in one guy during the, I'm going to say the epitome of the scientific revolution.
Sure.
I'm going to try and be brief, and if I'm wrong about anything, Paul's going to chastise me. If I go over on anything, hopefully Paul will chastise me. And if I'm too brief on something, hopefully he will clarify things, because Paul likes to pretend he knows something about science.
Yeah.
But it is all a show. Seriously, he doesn't know what the hell he's talking about.
You're just making this shit up as I go along.
The first thing we need to realize, though, is that the idea of gravity is intertwined with astronomy. Because, again, we didn't think gravity existed. Nobody thought about it for a very, very long time. The only time they actually saw anything about it, the only time it came into play, was planets. When you're looking at the sky, you look up there, you see, you see all the celestial bodies moving around, doing things. That's the only time you actually get to observe gravity. And gravity only really comes into play with big things. With small things, I mean, my pens are not being pulled toward each other on the desk. That's not really exactly how it's going to work. So gravity really only comes into play on very big things. The only time we experience gravity on Earth, per se, is the Earth, and it always goes toward the center, which is always down.
I would have to disagree with you. There is a gravitational attraction between the two pens on your desk. According to Newton's formula for gravity, it's the mass times the square of the distance between them times the gravitational constant is the force. So
how much force do you think the two pens on my desk are?
It's a number greater than zero.
It's a decimal.
I didn't say it was a number greater than 1.
Greater than 0.0000000000001 pounds of force. I mean, it's basically non-existent. And we're talking about ancient peoples who couldn't measure these things. Yeah, that's the equivalent of zero to them. Which is why when they're talking about gravity, they're talking about planets.
All right, fine.
All right. So the Greeks begin this. I mean, like most things, it begins with the Greeks. Consists of a bunch of Greeks looking up at the stars. The Greeks had what you call natural philosophy. It's like science without all the, experimentation. Just observation and deduction. The Greeks thought there were basically two ways matter could behave, in straight lines and in circles. And this way of thinking seriously guided philosophy for like 2,000, 3,000 years. I mean, it's really, really foolish, and it turns out partially correct, but not really. Now, they also came up with, again, through observation and deduction, the geocentric model, which eventually gets more codified under Claudius Ptolemy in the 2nd century AD, or I guess CE we're supposed to call it, the Common Era.
Sure.
So
Anno Domini,
the year of our Lord.
The year of our Lord. Maybe we can move past that.
Yeah, seriously. The next really important thing that comes from a Polish priest named Nicholas Copernicus. Before we go any further, I just want to make it fairly clear that gravity is the force which pulls matter toward matter. On Earth, you've got the planet that's pulling us down, and nothing else comes into play. So they're looking up at the stars. Copernicus sits there and he maps the stars. Now, he lived in the the end of the 15th, beginning of the 16th century. He was born in 1473. He had no access to telescopes. He only had, raw observation. Mm-hmm. Just sitting out there at night, looking up at the sky. Now, based upon his observations, he deduced that the sun was the center of the solar system without telescopes. I mean, Copernicus is badass. He comes up with this heliocentric model. Since it's heretical, he doesn't say anything about it.
He writes, talk about that shit.
He writes some manuscripts, keeps them to himself. Eventually, he sends them, anonymously to friends and other astronomers. Actually, nothing really happens till, after he's dead. But I mean, at the end of his life, he decides to publish his work called "On the Revolutions of the Celestial Spheres." It's said, no, we don't know if this is true, this is apocryphal, that he actually received one printed copy of his book on his deathbed, 1543. But, that's
nice.
That's the way the stories go.
It's a good story.
It really is. But he never really got credit for anything. Nothing really happened with his work until long after he's dead. The next guy that comes up on our list, which is one of my favorites, as historical scientists go, Tycho Brahe.
Tycho Brahe is one of your favorites, huh?
Oh, yes.
Okay.
He's a character. We could give him a show of his own. Basically, just to sum up the interesting things about Tycho Brahe, he lost his nose in a duel and used to glue a silver one to his face. He had a dwarf that he thought was clairvoyant, and had the dwarf, he kept him around the house as a court jester, and he had a pet moose that he kept in the house and gave alcohol to. Eventually, the moose died from alcohol intoxication and falling down a flight of stairs. So Tycho Brahe was a character.
Okay, I got to stop you right there.
Yeah.
We need to do next week's show on psychics so we can prove that they exist, so we can do the following week's show and have Tycho Brahe as a guest. This has to happen. From beyond the
I can channel Tycho Brahe.
All right. Well,
he doesn't speak Danish when he's channeled through me. He speaks English.
That's good.
But he speaks in rhyme, so it'll be nice.
That guy sounds awesome.
Now, he was an astronomy buff, and he discovered a new star at the age of 26, which was pretty unheard of because people have been looking up at the sky for a very long time.
Yeah, sure.
He got some clout for that. He financed himself a nice big observatory, in fact, the best observatory in the world at the time. He began mapping the shit out of the sky. He had amazing precision for some guy that, again, didn't really have telescopes. He eventually was banished to Denmark, from Denmark and had to move to Hungary, but that's a whole other story. Very exciting guy. Brahe did not like the Copernican model. He put the Earth back in the center of the solar system, had the moon and the sun going around the Earth, but everything else going around the sun. So, he was not a mathematician.
Okay.
He really thought the Earth was in the middle. The moon obviously goes around the Earth. He thought the sun went around the Earth, but he could tell everything goes around the sun. So he put everything else around the sun. It was a very complicated model.
We really fought hard on that whole
It really looks like the sun is going around the Earth. Doesn't it?
Yeah, it really does. But it does not look like the stars are going around the Earth. It looks like the stars are going fucking crazy.
Yeah, they're just going around.
This way, that way.
And don't even get me started on planets, which I believe the Greek word, the root word that planet comes from, is actually wanderer.
Yeah.
Because they would just go random directions. We couldn't figure out why they were doing what they were doing. But as I said, Tycho Brahe, not a mathematician. He observed, he documented the hell out of the sky, but he couldn't really prove anything. He had this theory, it wasn't good, whatever. He needed himself a good, solid mathematician. And he found one in Johann Kepler.
Oh, there you go.
Now, Kepler, mathematician, a teacher, he did the whole thing. Here in Kepler, we have calculation. He was a very smart guy. He really liked an elegant theory. He liked the Greek model with the spheres, perfectly round. And at 24, while teaching a lesson in geometry, he realized the ratio of the diameter of the two circles he was dealing with matched the ratio of the orbits of Jupiter and Saturn. Yes, just while doing his homework, this guy notices that. It's fantastic. After this, he starts fiddling with spheres. He makes models, starts building these basically Russian dolls of what the spheres would be like going around the sun, because he was, again, heliocentric, not geocentric. Now, there were only 6 known planets at the time. And he had all 6 of them mapped out pretty well, pretty good. It was almost perfect in its what do you call harmony. And he actually is known to have said that he felt like he had seen the mind of the Creator in the beautiful harmony of his spheres. So he starts collaborating with Brahe, who gives him all this data, just raw data. And Kepler,
Kepler, drunk moose,
mathematician, just starts taking this raw data and working with it. And he ends up having a lot of problems with his spheres, not the least of which is Mars. Mars doesn't fit. He couldn't make the sphere of Mars fit inside the others. I mean, it wouldn't box right. And he had physical models that he tried to cram them in there, and they didn't work. So he gets a revolutionary idea. Revolutionary. No one had thought of this in 2,000 years. What if they're not circles? What if they're ellipses?
Yeah.
And so he says, Kepler, and again, direct quote, "I was almost driven to madness in considering calculating this matter. I could not find out why they would rather go in an elliptical manner rather than a circle. Oh, ridiculous me." Yep. 2,000 years of history taken apart simply by math.
Yeah, well, that has happened time and time again.
Yep. You put in the, what do you call it? You put in the sweat. You put in sweat equity and you get capital out of it.
Yeah.
Based upon this, he finds out that, he comes up with 3 laws. Kepler's laws, they're called. They are, the orbit of every planet is an ellipse with the sun at one of the 2 foci. 2, a line joining a planet and the sun sweeps out equal areas during equal intervals of time, which means that during the small end, when you're closer to the sun, it actually takes less time to make the curve than the rest of it. And 3, the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit, which means basically the same thing.
Yeah.
It's actually a mathematical way of looking at number 2. But so he publishes these 3 in a couple of books, Astronomia Nova and Harmonices Mundi, at the ages of 38 and 48.
Those are good titles, I guess.
Well, they don't really flow off the tongue, which
Not
is kind
so
of a problem
not
that
so
I've got.
much.
They're a little clumsy. He took, his theory along with Brahe's data and basically made our predictions and our calculations of what's going on in the universe hundreds of times better. I mean, just made it phenomenally superior. Then Kepler dies, 1630 at the age of 59. So we've reached a pretty good understanding of what's going on in the sky.
Well, most of us.
Well, actually very few of us, honestly, but that's neither here nor
It's
there.
those who were not in Rome.
Yes, the ones in Rome said, nope, celestial spheres. That's all there is to it.
Yeah.
Now, over to the other line of reasoning. Captain Gravity himself, Galileo Galilei. Now, I'm not going to say he's the first real scientist, but he did corner the market on experimentation. He did a lot of experimentation. I mean, he spent years just throwing things out the windows of the Leaning Tower of Pisa.
Apparently.
Rocks, weights, chickens, francs, Sicilian. He didn't like Sicilians. Sicilians, just to see, how do things fall? How do they land?
Yeah.
Eventually, having problems, actually counting the amount of time, he decides to use inclines and balls. So he rolls balls down an incline and can time that much better than just dropping shit out windows.
And, just to point out the title of the show, Apollo 15. We actually, that actually did happen. We went to the moon.
Mm-hmm.
Supposedly.
That's what I hear.
But we went to the moon, and Apollo 15, they actually had a feather and a hammer, and they dropped them.
Yep.
And in the zero, in the vacuum that exists on the
space.
moon,
Yeah.
no air currents to mess it up or anything, they fell just as Galileo predicted at the exact same rate. They both hit the surface of the moon at the exact same time, proving Galileo's theory.
And again, that goes back into the sweat equity. He worked really hard. He dropped a lot of things. He rolled a lot of things. He timed thing after time. Science is boring. It's so boring. You have to do the same thing over and over and over and over. You have somebody else do it, and you do that. I mean, science is no fun in that respect. But,
And Josh didn't even mention the part where the mentoring professor keeps yelling at you. But anyway.
All right. Now, Galileo was not just famous for flinging chickens off, crooked towers and hick towns in Italy. No. He also began to goof around with the newly invented telescope. He got it about a year after it was invented. It was invented up in the Netherlands by some guys that you've never heard of. Or at least I hadn't, so I hadn't thought they were important enough to put in.
That would require research.
Yeah, so he started looking at the stars at the same time. He would look at the stars and drop things out windows. Mm-hmm. This is how Galileo spent his time. He also had a lot of literature. He had Copernicus. He read the theory. He had a problem with the theory in that the Earth has to spin. Well, if you drop things out a window and the Earth is moving, why do they land directly below the window? They shouldn't. They should actually land, according to his calculations, about a half a mile away. If the Earth is spinning at the speed he thought it would be spinning at.
Yeah, no, but we'll get there.
Right. Well, that's basically the problem that he had, and that's why Galileo is not Isaac Newton.
Yes.
His conclusion, which, it seems self-evident now, was that when a body falls the Earth together with the body move horizontally. They're both moving at the exact same time with the exact same inertia. They both maintain their horizontal velocities. Therefore, the body does not slow down with respect to the Earth and falls vertically down to Earth, which is what we observe all the time.
Yeah, there you go. He pretty much got it.
All right, so he goes and applies the same kind of reasoning to projectiles, cannonballs, that sort of thing, and starts calculating the speed and the arc at which they fall. But that's about as far as he gets. He does get famous, though. And so the scientific community has everything there is to know about Galileo. Mm-hmm. And the guy that gets that is Sir Isaac Newton. Newton was born in 1643. And just a point of interest to anybody out there that cares, he personally told at least 4 people about his apple falling out of the tree story. He wasn't sitting below the tree and got hit in the head with it, but he did watch an apple fall and start thinking about Galileo's theories. So there is, a grain of truth in that. Newton was always thinking about how bodies move. Now, keep in mind, again, gravity did not exist at the time. There was no such thing as gravity. Things fall down.
Yeah.
That's all there is to it.
Yeah.
Gravity as a concept was unheard of.
And the idea that, things fall down, that's universal. I mean, we now know that when you're, in the space shuttle or you're in the International Space Station, you float around in what we call microgravity. If you were further away, like halfway to the moon or such, you'd be in a completely weightless environment. Right. That idea didn't exist. Like,
nope.
Things fall down.
That was, again, it was like the circles that everything travels in circles. Yeah. It was just unquestioned. Yeah. Things fall down. Nobody bothers to study it or examine it because it's self-evident. It's axiomic. Premise 1, things fall down.
Yes.
Newton was always thinking about how bodies move, though. All right? He was always considering this. Now, there is some drama with a guy named Robert Hooke who claimed that he was actually the inspiration to Newton's theory and a whole bunch of other crap. He sued him. He got written about in the preface. But, neither here nor there. The guy didn't actually do anything of any real import. Again, they knew that things fell down, and because of Galileo's experiments, they know exactly how fast and in what way things fall down. A friend of Newton's, Edmund Halley, of comet fame, actually carried a pendulum to up the top to a 2,500-foot hill and tried to calculate how quickly it actually swung. Did it swing at a different speed? Mm-hmm. And truth be told, it actually did.
Okay.
So, it gave some credence to the concept that when you're closer to the center of a mass, there's more of a pull.
I see what the experiment was, yeah.
Right. So nobody knew what this pull was, though. So Newton knew at the time, now from Kepler, how planets were moving, and that the inverse square law might cause a body to move on an ellipse. So Newton had this because of Kepler. I lost my spot. Yes. But in August 1684, when Newton was 41, Halley put a question to Newton. Supposing an inverse square law of attraction toward the sun, what curve would a planet make? Newton then said an ellipse, but, he went out calculating on this. Now, he began this when he was 23. He started working again on it with the proofs and doing that sort of thing, and it proved hard because there's actually... it wasn't a concept that we were familiar with. The idea of gravity didn't exist. It was difficult to describe. So Newton invented a vocabulary. He defined quantity of matter as mass, quantity of motion as the product of velocity and mass. Mm-hmm. We've actually come down to have better ways of saying that now. He then sends Halley a 9-page treatise on the motion of bodies in orbit. Halley was excited, asked Newton for more pages, but Newton wasn't finished. But in 1686, at the age of 44, Newton gave Halley Book 1 of Philosophiae Naturalis Principia Mathematica, which is the book. It's the great book. That's the invention of gravity.
The good book?
The good book, yeah. What? More accurate. But that's the invention of gravity. It was this book that actually calculated everything. And it included a lot of stuff aside from gravity, but gravity is the thing we're concerned with now. Now, what exactly did Newton do? First, he found these laws that explained the previous discoveries of Kepler and Galileo. People suspected the laws, but no one was actually able to prove them. And based upon their earlier stuff, Newton came up with the idea of, if I've seen further than others, it's because I've stood on the shoulders of giants. because these were giants at the time. I mean, Newton's the badass, but these people actually did all the work.
Yeah, well, Newton
that he leached off of.
Newton gets a lot of credit. Newton deserves a lot of credit, but so do all of these people who led to this. It's not like. I'm serious when I say this. It's not like Newton himself invented Newtonian physics.
No, he stole other ideas, put some disparate ideas together, and did a lot of math.
Yeah.
What did he say? 90% perspiration, 10% inspiration?
Sure.
Yeah. I'm going to say that was Newton. That's what I'm saying. His inverse square law explained the ellipses that make the planets that Kepler realized act the way they did. And he also came up with, force equals mass times acceleration. But he put in there force being the newly found gravity. This explained the motion of the objects on the Earth that Galileo discovered. Second, he generalized his theory. He realized that the same laws apply here on Earth are the ones that are going to apply in space, up on the celestial bodies. So he's the first person that actually connected those two things properly. Galileo tried, but really didn't have the math to back up his claims. Mm-hmm. And in this way, he actually was the first person that actually unified the theories. And we keep unifying more. I mean, electromagnetism, the nuclear forces, and we're trying to get gravity in there. We're trying to shoehorn that bad boy in there somehow.
Yeah, we are.
He also was able to mathematically show exactly how the tides worked. Because we all kind of knew the tides had something to do with the moon. He actually was able to calculate how the tides worked.
Take that, Bill O'Reilly.
Yeah. Tide goes in, tide goes out. You can't explain that. I can. I'm English, and I like apples, and I can actually explain exactly why that works. Yep. Now, the problem he had, and this is a problem that people have actually had for quite a while, and we actually have a problem similar to this in quantum theory right now, but the problem he had was action at a distance. I mean, it was a bitch. He didn't like the idea that things could act upon each other without being near each other.
Yes.
In fact, being really far from each other. But he had math. He had lots of math. And it worked. Obviously, it was true. Why? Who knows? But it's true. There's something that's happening. Now, this is not only force equals mass times acceleration, but it's the law of universal gravitation. Every point attracts every single other point mass in a force pointing along the lines intersecting both points. The force is proportional to the product of the two masses and inversely proportional to the square of the distance between them.
Yes.
So that's,
And to actually figure that out, there's big G.
Yes, there's F equals big G times M1 times M2 over R squared.
Big G being the gravitational constant,
yes.
Little g being the force of gravity, the acceleration, I apologize, the acceleration of gravity at sea level on Earth, which is 9.8 meters per second squared.
Yes, indeed.
But big G.
This is big G.
Yeah. Big G is that's the universal gravitational constant.
So here, force is the force between the masses. G is the gravitational constant. M1 is the first mass. M2 is the second mass. And R is the distance between the centers of the two masses. So we've got a very simple, very elegant formula that works.
Yeah.
It works really, really well.
It really does.
So there you go, folks. That's why we can't fly.
Well, I was gonna mention that. I was gonna talk a little bit about Douglas Adams.
Well, falling toward the Earth and missing.
Yep.
Well, we can talk about satellites in a moment. All right. The formula stood as the end-all to gravity studies for a couple of hundred years, until Albert Einstein comes along. Now, there were some tiny, itsy-bitsy discrepancies that didn't fit Newton's theory. Mercury, for instance. Mercury was a son of a bitch. They couldn't figure it out. A lot of people thought that it was because Mercury was so close to the sun that the rules were different somehow. Mm-hmm. And that didn't seem to actually work, because Newton's theory works for everything else, except these tiny multiple points past the decimal. It just wasn't quite perfect. So, in 1916, Einstein finds a good theory that would explain it. This is actually based upon the 1905 stuff. Back in 1905, Einstein managed to extend Newton's theory of motion of bodies at high speeds. But this is assuming, and this is where he invents it, a constant speed of light. And that means that light's always going the same speed, whether you go away toward it, away from it, sideways, doesn't matter. Light's always going the same speed. The results were valid only if the objects were moving at a constant velocity. So in 1905, that's what he was able to do. The problem is, what about when they're accelerating? So this caused him some problems, which is why in 1916, with 10 years and lots of think horizon, he comes up with an answer. First, he assumes that a person cannot distinguish whether he is in a gravitational field or under constant acceleration. You know, like the flat earthers think. So these two things are basically equivalent. The assumption provided a link between gravity and mass, or as they say, gravity and energy. He concluded that mass and energy must affect gravitational field. Second, he stated that the gravitational field is not actually a force as Newton had described, but instead a curvature in space. Simply put, the bodies are affected by gravity not because a force directly exerted on them, but because space is curved, and therefore they have to follow space's grid. The grid being curved, therefore things go toward the slope. I mean, if anybody's ever seen the picture, or the picture we've got for our episode today, it's curved space.
Yeah, imagine a piece of saran wrap that has like say a billiard ball on it. If you stretch out the piece of saran wrap, and this is in 2 dimensions. You know, the universe is in 3 dimensions. It's a 2-dimensional example. You take the billiard ball and you put it on the saran wrap, and it's going to curve in the saran wrap around that. And if you were rolling a marble around that piece of saran wrap, if you got close enough to that curve,
it would tip over.
It'd fall into the billiard ball.
All right. Now, Earth always moves in a straight line. Not in the Euclidean sense, though. The presence of the sun curves space and therefore curves this straight line and forces Earth to appear to be moving in an ellipse, going around the sun. Since mass curves space, then the objects just move on this space. There's no reason why, for example, light couldn't follow space's curvature. So this is when we start bending light.
Oh, because light has mass. Because photons have mass, right?
Don't even get started. Don't even get started.
Hi, Paul.
One of Einstein's first ideas was that light should be able to bend too when massive objects are close to it. The problem is the only thing we've got really massive that we can actually look at is the sun. You can't look at other light sources when the sun is out because you can't see anything. All you can see is the sun. So, he made some interesting calculations, and it was a good idea, but they couldn't really test it. They tried it during one eclipse, and it didn't really work out. Then, a bunch of German scientists went to Russia for an eclipse, and they did some goofiness, and they found out, yes, it does work. Mm-hmm. The sun bends light. So Einstein, proven right. Einstein's on the front page of all the papers, becomes most famous scientist in the world. It's not actually what he won the Nobel Prize for, but that's neither here nor there. So that's the history of gravity. There's a long preamble to Newton. Newton invents it, and then Einstein perfects it. The problem is that a lot of people think that Einstein actually revised or corrected Newton's theory. That's not entirely correct. Newton's right.
Yeah.
I mean, Newton is correct. Well, Newton's accurate. I won't say right, because, science, we don't, right and wrong are Newton is accurate. So we've got this all figured out. I mean, gravity, we're done.
Sure.
End of story. We're fine.
Problem solved.
No. Apparently, quantum theory shows us there may be a couple of teeny tiny tweaks left. General relativity seems to be basically incompatible with quantum mechanics. It sort of breaks down theoretically. In most cases, gravity is so weak that on teeny tiny itsy bitsy small scales, like particles and shit, it's basically ignored. Actually, Paul, you may be able to help me. I mean, you're the one that explained quantum theory to me. You may be able to help me out a little bit on this. Basically, we've unified electricity and magnetism. We've figured out the strong and weak nuclear force. We've just got gravity sitting out there.
Yeah.
What's the deal?
Well, there's, okay. I will first off have to say I know a little bit about this, but there is a reason why I became a chemist and not a physicist. Some of this shit is just, it's a little crazy. Okay, so all of the other forces, we figured out how to put them in a box. Now, what I mean by that is whatever it is, whatever the fluffy shit that you believe from what you've heard about, the Heisenberg uncertainty principle and Schrodinger's cat and all of that stuff, quantum mechanics is nothing more than saying at very, very small lengths the universe is quantized, meaning it's pixelated like a television. Mm-hmm. When you look at your television from far away, it looks like a whole picture there. But if you get really, really close to it, you see it's a little tiny box of the color blue and a little tiny box of the color red.
Right.
And that is basically what the universe is like as you zoom in closer and closer and closer. Mm-hmm. And where this came from was electrons. Electrons have discrete energy levels. This was figured out by a guy named Max Planck. And Planck figured out that the smallest distance that there can be is, where is it? 1.626 times 10 to the negative 35th meters.
If only someone could name that after someone who would have discovered it. What's that called?
That would be the Planck length.
Ah, yes. I'd name things after myself.
So you think you're walking across the room, you think you're moving smoothly in space. You're not. You're actually disappearing and reappearing 1.26 times 10 to the negative 35th meters forward. So there's where these boxes come in. And these boxes make everything make sense in terms of the strong and weak nuclear force and a lot of the particle physics stuff that I'm not even going to mention because Brian will kill me. Except for gravity. Gravity there's theories, there's hypotheses, there's some ideas. There's something called a graviton. We can't find it.
Gravitons were famous for a while. They came out and people loved the graviton.
Yeah.
But then nobody could find it. They said, we're going to give up on gravitons.
And ultimately, all of this, micro universe aside, the real problem with quantum gravity, with trying to make a grand unified theory, in order to do that, having to fold quantum gravity into it, the problem is gravity appears to be non-renormalizable. Mm-hmm. Non-renormalizable.
Yeah, that's fun.
Let me just tell you real quickly what that means.
Thank you.
Renormalization is a collection of techniques used to treat infinities that arise in calculations. So it's kind of like, you have a formula and we're talking about all these quantum mechanics formulas where now you have an infinite number and you have to treat it somehow. And you do renormalization to basically make it go away and you get the answer that you want. I'm sure there's a better explanation for that, but again, we probably don't know what the hell we're talking about.
Yes.
The problem with gravity, as far as we can tell, is that there appears to be, of those infinite variables that you can renormalize, there seems to be an infinite number of infinite variables.
That seems to be a problem.
Yeah.
Infinite infinites? That doesn't seem like that's good math.
So,
that's not elegant, as they say in the physics community.
I mean, and that's the best I can come up with as a non-physicist, as someone who has a fair understanding of quantum mechanics as how it applies to the atom, as how it applies to electrons and things like that. But we didn't touch on gravity in any of my PhD work for medicinal chemistry. Gravity wasn't really a big thing that we really got through. So that's the best I got. It doesn't make any sense, and again, quantum mechanics bothers the fuck out of me because
all the basketballs?
All the basketballs. Because it doesn't make any sense. People are using it to whatever means that they want to make it spiritual and blah, blah, blah. But in the end, I expect that we'll figure something out. We'll figure something out.
There'll be a lot of calculation, and who knows, maybe we'll have another Einstein who comes in and says, yeah, you guys are all correct, except here's the thing. And it'll be a slightly new perspective, which will unify everything. It'll be beautiful.
Or we'll just come to the conclusion that you can't unify everything. Maybe. I don't know.
Nah, we're never going to come to that. We really started unifying things and thought, man, that kicks ass. We should keep doing that.
Unification.
So unification. It's science. Monism.
Yeah. So ultimately, quantum gravity, boy, I don't know. Quantum entanglement does actually answer the question that was originally asked by, I think you were saying Newton.
Yeah.
The idea of how do they interact if they're that far apart?
Right. That was his big problem. He still didn't get Einstein kind of explained that, but not fully.
Right. Well, quantum entanglement, which we know little to nothing about, except for the fact that we can impart something to a particle, like a specific controlled spin to a particle, and the same thing will happen to a particle that it's been paired with.
No matter how far apart they are?
No matter how far apart they are.
Which seems absolutely crazy to me. It seems like madness.
And I don't think we know why the hell that happens.
Not yet. There's some theories.
Yeah.
They seem to fall apart the more in-depth they get, though.
And that ultimately may have something to do with this whole gravity thing. Maybe that makes sense. At least we've solved the communication over a distance problem. Mm-hmm. But that's all I got.
All right. Well, hopefully that explains quantum gravity to anybody out there. Everybody's going to say, well, that makes perfect sense now.
It's clear.
The answer is, I don't know.
Yeah.
Okay.
Sure.
But nobody knows, so I don't feel too stupid.
But I have faith.
I have faith, too.
Yes,
I have faith in your faith.
You have faith in my faith about my faith on quantum gravity.
No, I have faith in your faith on my faith in faith.
That's reasonable.
Okay.
That's exactly reasonable. That's exactly why we do the show, to
that's how I roll.
generate and create reason. Intelligently designing reason. That's what we're here for.